All right, so good evening. Welcome back to the weekly tutorial sessions on wheel mobile robots. I'm Isaac John, and we are here to discuss some sample problems with respect to the topics that we have covered in week 5. So I hope so far, whomever is attending the course, I hope so far the course has been going very well. I hope these weekly sessions are helpful, for solving the tutorial problems. Uh, okay, so just like before, the way that I have set up these sort of sessions, we since this is a 2-hour session, I thought it would be a good idea to dedicate, the half of the session for discussing a brief summary of all the topics that we have covered, for the course of week 5. And then for the remaining half, maybe we'll discuss some sample problems, which is very similar to the quizzes that you can expect, uh, you know, uh, you can expect for your certificate exams. Uh, yeah, so as before, the first part is mostly, I would be mostly delivering my internal monologue because most probably there won't be much of an engagement. But, in case if you have any doubts regarding the topics that I'm discussing, or if you have any general doubts, or those who are attending the current session, if you have any sort of doubts, please feel free to, interrupt me and we can have a discussion, you know, whatever be the topic. So, without much further delay, we would get started with our discussions. So, now that we have covered, halfway through our course, let's have a quick summary of what we have covered so far. So, in week 1, it was more or less like a general overview of mobile robots, right? A general overview of mobile robots. Then for week 2, we basically covered, kinematic modeling of wheel mobile robot. We have essentially covered, how the kinematics would look like for different wheel configurations, right? We have seen, how to construct, or, how a differential drive robot moves, or how a robot with 3 omni wheels move. We have also seen how a robot with, three mechanism wheels would 4 mechanism wheels would move, and how these are advantages, how one system could be advantages, or compared to the other one. We have also seen the difference between, a holonomic system and a non-holonomic system. So those are the topics that we have covered for week 2. And for week 3, we have discussed dynamics, right? These are basically the governing equations of a robotic system, right? Like if you supply a force or an input to the system, as torque to the motors, how would the system respond? What are the trajectory of that? How would the system respond to that input that you're giving? So we dedicated ourselves to deriving the equations of motion, or the governing equations of motion. We have seen two different approaches. The one we call the Euler-Lagrange method. We derive the equations of motion through energy methods, and the second being a more comprehensive but more systematic Newton-Euler approach. So that was about week 3, and for week 4, we have discussed topics about perception, right? So stepping away from mechanics, uh, or in short, what we have covered up to week 3 was mechanics of robot. For week 3, the kinematics and dynamics, they constitute the branch what we call as mechanics. And from week 4 onwards, it was more or less like a shift, where in week 4 we discussed perception. We discussed, what are the tools that a robot would require for perception, right? All sort of sensors that we will be using. We have seen the classification of sensors, whether it is a whether the sensors can be classified as a proprioceptive sensor, which are internal to the robot, or whether sensors can be classified as, exteroceptive sensors, the sensors that are mounted external to the robot, to sense the change in environmental parameters. Then we could also classify the sensors as active sensors or passive sensors. Where the active sensors where you have to supply a power source so that the sensor can emit some sort of an energy and measure its reaction, right? Those who are active sensors, and those who does not require any external power source, we could call them as passive sensors. So now that we have covered the perception, the next important stage that we would discuss uh, for the duration of week 5 is something what we call localization, right? So like once the robot has uh, muted myself, I hope I'm audible. I hope I'm audible. Uh, okay, let me check through the chat if I'm audible or not. Okay, thank you for confirming. All right, so for the last week we have covered this part. The part we call the perception subsystem. Where we would use sensors over here to to have a good understanding of our environment. If you want to see if there are any obstacles near our robot, or if there are things that could be of interest. We could use the robot's cameras, the lidar sensors, or even proximity sensors to have an understanding of the environment. So that part was perception. And now once it has gathered information from the sensors or extracted data from the sensors, the next stage is what we call localization, right? So localization and map building. So this is the phase that we were covering for week 5. And the purpose of this stage is that once the robot has gathered data, the robot will have to create a map, for its own reference, a map of its surroundings, complete with all the obstacles, with all the features, or the obstacles could even be dynamic. So the map is also the map should also be dynamically updating if there are dynamic objects within the map. And simultaneously, when it has created a map, so if you consider this to be a map of the environment, with multiple objectives, the robot should also locate itself, within the map, right? The robot should know where exactly its position is within this map. So that process is called localization, right? And yeah, that is the topic for our discussion. And yeah, for the period of this for the period of this session, we would be having a brief overview of what we define as odometry and dead reckoning, and there's something called map-based localization, where you would feed a map. A user would feed a map of your environment, and the robot then will plan accordingly based on the map that we are giving as an input. So there are two schemes that we would use. The first one being the Markov localization, and the second being the Kalman filter localization. And there is also a separate scheme where it's something called autonomous map building, right? So here the map building as well as localization, they happen simultaneously. So no map is preloaded into the robot. So the robot, as it moves through the environment, it creates a map of its own. So you might have seen the vacuum cleaner robot, such as the Roombas. They we are not supplying the map of our room or our home into the robot. The robot itself will move around, and then it will basically create a map on a map onto which it is deployed. So yeah, these are the basic topics that we will be discussing for the duration of this session. Yeah, and let's see what are the important steps of localization. So we'll basically begin with this stage, prediction of position. So like, for example, if you consider your robot to be in this position, like I'll just draw a coordinate system like this. Right? And if you consider at time t, this is where the position of the robot, xt, at probably the time t, right? If you consider this to be the position of the robot at time t, uh, we are also giving some sort of an input to the robot, in the form of actuators, in the form of motors, ut, right? So basically, the robot would predict its new position, right? From the current position based on the input that we are giving into the motors and based on the proprioceptive sensors that it has. The first thing that you can think about is something called an encoder, right? An encoder basically measures how many rotations the wheel has rotated. So, if you apply some input into the motors, the motor would rotate the wheels, and the rotation of the wheels can be measured using these encoders. And based on the current position and the encoder signal, the robot would basically predict. The robot would basically predict where its next position should be. So, with a compromise accuracy, the robot would predict that, somewhere around here is where its new position at time t plus plus one, right? So I'll also draw the perspective from a map. So if this is a map, right? Earlier, the robot was here at time t. And if you give a control input like so, the robot thinks or the robot predicts that, this is where its position is going to be at time t plus one, right? You can consider it already has this map. It already has fully. We have already given a full map for this. All right. So once the robot predicts its new position, what it does is that it basically estimates its position based on its map, based on the map it gives. Then what does it do? After it has reached its position, it just gets its data from the sensors. It'll open up its eyes, or sensors that is similar to eyes, maybe some ultrasonic sensors or some vision sensors or some lidar sensors. Then it will see. Then it will basically probably map its position based on some landmarks within the map. So if you consider these are, definite features on the map, then the robot tries to see, where its position is based on the distances from, each of these defining features, right? So what it does is it basically estimates or basically it tries to match its prediction, what it predicted using its map and using its input. And it compares that with what it actually sees using its sensors, right? So the data coming from the sensors and the data coming from the map as a result of prediction, the robot basically does some sort of a matching. So if both of them are correlated or both of them are exactly mapped, then the robot does not have to adjust its position, right? Whatever coming from the sensor is the true position, and whatever predicted from the map is based on, what it can predict from the previous stage. But the prediction may not always be true because, there could be issues due to, wheel slipping. There could be issues due to, mathematical round of errors. All these sort of things can creep up through the prediction phase. But the observation phase is actually what it really sees. So it does a matching, between the predicted information and the perception information or the data from the sensors. And if it is, if it is happy with its estimate, it does not do any sort of thing. Or if there is some slight mismatch, it will give some corrective actions so that the new position of the robot can be achieved, or the desired position of the robot can be achieved. So then this thing goes on and on and on as a continuous loop for all the time steps. So like for x as t plus 1, this thing goes on for t plus 2, t plus 3, all the way until it reaches its goal position. So the key things that you would want to understand is something called odometry. And odometry is something. Odometry is basically the prediction phase, right? If it is using the information just from its encoders, you know, like for example, if you have a differential wheel robot like this, right, and you have two wheels, and each of these wheels will have encoders, used to measure how many times these wheels have rotated. So based on the number of times each of these wheels have rotated, the robot can predict where its next position should be, right? Well, one example is that if both of the encoders are giving you the same data, it means that the robot moves in a straight line. And based on the number of pulses that an encoder gives, you can also calculate its amplitude. So, estimating the position based on the encoders is what we call odometry. And if you use the heading sensors, apart from encoders, if you use heading sensors like gyroscopes or inclinometers to know, the heading or the orientation of the robot, that is something what we call as dead reckoning, right? To know where the robot is headed to, or to know its position, the next position using just the sensors, uh, like the gyroscopes or the inclinometers. That process is what we call dead reckoning. And odometry is for estimating the position just by using the sensors. So, what are the challenges that is faced by localization? So the first is actually, knowing the absolute position. Like, a GPS is not really sufficient, right? Because a GPS's uncertainty is actually pretty huge. It cannot pinpoint you by exact millimeters or even by feet, right? It'll probably give you a scale based on meters, but it's still a fairly large uncertainty when you regard a mobile robot, right? Because if you deploy a mobile robot in a room, you probably want to have accuracy to the scale of centimeters or even millimeters. So GPS is actually not an option, and that is also a GPS is probably not even suitable in indoors as well, right? If you talk about a huge industrial building, it might be probably difficult to get signals from GPS. So that is not an option. And yeah, the second option is localization in human scale in relation with the environment. So like a human scale is somewhat very small, right? It's much more smaller than when you compare with the uncertainty radius of the GPS. So in case of a mobile robot localization, it has to be in the scale that is relevant to a human scale, or how much a human moves, or how fine a human being can you know move within an environment. And the next stage is planning in the cognition step requires more than only position as input. So just a position itself is not enough for planning the next step, right? You need to know more about if you just have a position, that itself is not really enough. You need to know about the uncertainty in that position estimate, right? Because if you are purely using odometry, if you know the current position, and if you're using purely relying on encoders and heading sensors to estimate its new position, probably as xt minus one, whatever you are estimating from the control input, it need not be accurate. There is an uncertainty associated with the estimated position, right? Because as you know, you cannot really fully rely on the encoders, right? If your wheel is slipping, the encoders would still give you a large amplitude, but the robot won't be moving any further because the wheel is actually slipping on the ground. So if the encoders predict that the robot has moved 5 meters, and due to the wheel slipping, the actual position of the robot would be, it probably might not even have moved, right? So that is the reason why we have an uncertainty. So, just the position as an input is not really suffice. We should also give out an uncertainty measure, associated with that position. And then there are several other challenges associated with sensors. Right? This thing was prediction actually, challenges associated with prediction, and there are issues associated with sensors. Right, the first one being sensor noise. Right, so like if you can recall, there is something that we have discussed in the previous week. That is something called cross sensitivity of the sensors. Right, that is something, cross sensitivity is basically the sensitivity of a sensor of parameters that are orthogonal to the things that we are trying to measure. Right, so like if you are, for example, like if you are trying to measure temperature, uh, that measurement could be probably influenced by a lot of other factors, maybe the wind speed, probably the humidity, all these sort of things. It could be, it could be influenced. uh, yeah, sensor noise, that is one challenge. Then there is something called sensor aliasing. So usually, to measure one parameter, we would rely on multiple sensors, not just a single sensor. Because a single sensor, the measurement from a single sensor is not very reliable because it has a lot of noise, and it also has a lot of uncertainty associated with it. So what we do is we rely on multiple sensors for measuring a single parameter, and then we would fuse the data from all the sensors to have a reading with lesser uncertainty, right? So like as you are getting more and more information from different sources, the uncertainty basically reduces, right? Because it's something very intuitive to understand. Then there are things called effector noise, noise due to the motors. The motors would not be perfectly moving. And then there is something called, the thing that we have just discussed, the odometric position estimation. If you purely rely on odometry without without any sort of inputs, that just means that you are moving in blind. You are not relying on any visual, or sorry, any sensory feedback from the environment. So those were the challenges uh, uh, for localization. Then we have something called errors, odometric error sources. Like I was mentioning, we cannot fully rely on odometry because odometry comes with a lot of uncertainties, and this uncertainty is actually uh, the factors that are contributing to these uncertainties are these error sources, right? And the based on these sort of error sources, we you can classify these sources into two categories. The first one we call them as deterministic errors or systematic errors, and the second classification is what we call as non-deterministic errors or non-systematic errors. So in deterministic errors, we can exactly predict its magnitude. We can exactly model the error in a deterministic way. How much error that is going to be. How where that more error is exactly going to happen. So like I'll give you a simple example actually. So if you have a differential wheel robot like this, and if you have two wheels, right? Uh, and for the time being, we'll consider both of these wheels are of the same diameter. They are exactly identical, perfect to the geometry. And if you give an input of equal magnitude to either of these wheels, maybe I'll give the input as omega and omega. Both of the wheels are being given a constant magnitude input, that too in the same direction. we expect the robot to move forward, right? In a single direction, in a constant direction, right? That is expected behavior, nothing surprising in that. But what happens if the radiuses of the wheels are not, if the radius of the wheels are not perfectly equal, right? So like if I call the radius of the first this wheel to be A1 and this wheel to be A2. So even if you give the same inputs, the velocity on this side would be A1 omega and the velocity on this side would be A2 omega, right? So even if you give the same angular velocities to the motor, the velocities at the periphery of the wheels would be different because of the difference in the diameter, right? So by giving this constant uh, inputs, we expect the robot to move in a straight line. But due to the change in this radius, the robot, you can basically see that the robot would move in a curved manner. Depending on the size of the radius of the wheel, it could move in a curved manner as opposed to a straight line. So what we can do is that we can exactly measure the change or the change in the radius. We can measure it to very high accuracy using micrometers, vernier calipers, screw gauges, all these sort of things. We can exactly measure the radiuses, and if we can exactly measure these radiuses, uh, we can then plan the input accordingly so that the robot would move in a straight line, right? So given that we have exactly estimated these radiuses, we can basically decide on how much this input has to be. So then the new velocities would be A1 omega 1 and A2 omega 2. So A1 omega 1 would be of a magnitude V and A2 omega 2 would also be a magnitude of V. Both of them has the same magnitude, and the robot would move as you would want it to move, right? In a straight line. So the reason is that, like, if you are able to exactly model or if you can exactly determine these sort of errors, right? You can incorporate that error in your model, and you can basically give your control inputs accordingly. So those sort of errors where you can accurately model these sort of errors are something what we call as deterministic errors. Errors that you can uh, deterministically model. But this is just a hypothetical scenario. What we do actually in practice is we refine our models, we refine our robot's wheels in a way that both of the wheels have exactly the same diameter or radius. They are of we can manufacture them to be of very high tolerance, right? So that both of the wheels are almost equal diameter. So this is also another approach, right? Instead of accommodating the errors into the model, we can eliminate the model. Sorry, we can eliminate the errors, right? By refining our manufacturing processes. So those sort of errors, where you can model it and accommodate it in your model, or the errors that you can eliminate it, through proper calibration. Those sort of errors are what we call as deterministic errors. And errors that we cannot do either of them. We cannot model them deterministically, or we cannot even eliminate them. Those sort of errors are what we call as non-deterministic errors. Right. So let's see what these bullet points are. These are just extracted from the lectures. So deterministic errors can be eliminated by proper calibration of the system. Okay, that's what we have basically discussed so far. And non-deterministic errors have to be described by error models and will always lead to uncertain position estimate. So, you cannot exactly model, but, non-deterministic errors, you can model them as a probability distribution, right? Not exact, but, you can model them probably as a as a Gaussian distribution with a mean, mu, and a variance, sigma. Yeah, with a variance sigma. So every time you have an order, you have an error. You can expect that error to be within this bell curve. If you assume your error to be following, this sort of distribution, or a Gaussian distribution. All right. Um, then what are the other sources? Yeah, we also see the major error sources in a wheel mobile robot. So the first thing is limited resolution during integration. So this is not a deterministic error, right? This is basically a not deterministic error because we can only improve the resolution of integration so far. Thus, only so far. We cannot we cannot refine this integration any higher, any higher more than the sensor, more than the sampling rate of the sensor, right? Because the integration that we are talking about is a numerical integration, based on the sampling rate of the sensors. So like if the sensors sampling rate is of is of a given units, or if is of a given interval, you cannot actually eliminate this sampling time, right? Every sensor will have a sampling time, and because of that, there is actually a limitation in integrating it, actually limited resolution during this integration because of the sampling time. So any errors due to very large sampling time cannot be really eliminated, right? We will be essentially missing a lot of features in between this sampling time, right? We can only extract data here discretely like so, but whatever information that we have in between, we are basically we cannot exactly predict that, or we cannot exactly capture that using integration. So that is a source of a random error that we cannot fully eliminate. The second thing is misalignment of wheels. This is a deterministic error, right? We can always measure how much that particular wheel is misaligned, and take that into our, consider that into our model. Or we could remove that misalignment and make the wheel properly aligned using proper calibration. And another thing is unequal wheel diameter, the thing that we have just discussed. Either we can take that into our model, the effect due to unequal wheel diameters, or we can make them equal using proper calibration. So these are two deterministic errors, where we can fully eliminate that. And what about this one? Variation in contact point of the wheel, right? That is something that we cannot fully control, right? It depends on the environment, and we really cannot control the environment as per our requirement, right? The contact point of the wheel. So that is always not under our control. We cannot really do anything about that. And the same thing, unequal floor contact. Just like as I was saying, the robots, we do our modeling based on the fact that the wheels roll without slipping, right? The wheels will be perfectly rolling. But in real cases, you expect the floor to be slipping due to the characteristics of the wheel and the characteristics of the floor. We can control the wheel characteristics up to some extent, but the floor's characteristic, depending on the environment, we cannot do much about it, especially if the robot is deployed outdoors, right? Outdoors in the open environment. We cannot do anything about the contact, the floor contact. So that is about the error sources regarding error sources that you can expect in the odometric process. Yeah, so now we'll discuss odometry in detail. So odometry is, basically nothing but estimation of the new position based on the current position and the input, right? So I'll just write it as P dash. This is the estimate of the new position. This is equal to the, uh, yeah, estimate of new position is nothing but the estimate of the current position, that is, I call this as P, plus maybe a function of the inputs, maybe I'll call this input for the left wheel, sorry, the right wheel, delta SR, the input for the left wheel, that's delta SL, and probably the input for the orientation as well, delta theta. Or I'll just simply restrict it. If you consider a differential robot, these are basically the two inputs that you can give, right? Input to the right wheel and input to the left wheel. So I'll just give a brief definition for this. P dash is nothing but the new estimate of position, and this P is the current estimate or the current position. And this third term is nothing but the inputs, a function of inputs. So odometry is basically a prediction of your new estimate based on your current position and your function of inputs, right? And as I was saying earlier, this is just an estimate. It does not have to be accurate, right? Because in case of a wheel slipping, this prediction could be way off if the wheels are slipping. All right, so let's basically see what these equations are. So this thing, the effect due to the input, effect on the position coordinates due to the input, we call them as delta P, right? So these are all vectors basically. This P dash is a vector, this P is a vector, and this delta P is also a vector. So what are these vectors constituted of? So this P dash is nothing but the new position, x dash, y dash, and theta dash, right? Because you need three coordinates to fully describe the position and orientation of a mobile robot, right? You need two coordinates to describe the position of the robot, which are x dash and y dash. And you need one more coordinate, theta dash, to estimate its orientation, right? So all 3 degrees of freedom are required for a mobile robot. So this is nothing but x dash, y dash, theta dash is nothing but x, y, theta, from the previous estimate plus delta x, delta y, and delta theta. So this is due to the effect of inputs through the actuators. Right. So let's see what this delta x, delta y, and delta z are. So before that, let's see something. What we define some parameter called delta s. Right. Delta s is basically the incremental change of incremental motion of the mobile robot along its longitudinal axis due to the contribution of the actuators. So one thing I can show is that if you consider this to be the body of the mobile robot, and if you consider this to be the left wheel, left side, and if you consider this to be the right hand side, right? So if you consider the input to the left wheel, incremental input to the left wheel as delta SL, and if you consider the incremental input to the right wheel as delta SR, right? What will be the incremental motion of the mobile robot from its sender with respect to the from the sender, delta S, right? So if you do this simple interpolation or extrapolation, this delta S is nothing but the average of delta SL and delta SR, right? If you consider this to be the center line, this delta S, if I call this arrow as delta S, right? So this delta S is nothing but delta SR plus delta SL by 2, right? So if you consider this to be a trapezium, right? This is a trapezium, right? And the length of this larger side is delta SL, and the length of this smaller side is delta SR. The height of this trapezium, right? Height of this trapezium is nothing but an average of the two parallel sides, which are SL and SR. So that is what we have as delta delta S, what we call as delta S. So that is one thing, delta S. And another thing is what we call as delta theta. Or if you want to know what that is, it's nothing but the incremental rotation of the mobile robot with respect to this z-axis, very incremental rotation. So by definition, delta theta is nothing but it's given by this formula, delta SR minus delta SL by the whole divided by B. Right? If you consider the wheel to wheel distance to be B, this delta theta is nothing but delta SR minus delta SL by B. And delta SR is positive because delta SR would make the robot to rotate in the counterclockwise direction. So we consider counterclockwise rotation to be positive as per our convention. And delta SL would make the robot to rotate in the clockwise direction. So that would, by convention, that is a negative rotation. So that's why we have a negative delta SL over here. And this B is nothing but the track, or the distance between the two wheels, called B. So this is nothing but the superposition of theta as the arc by a radius. It's so this formula is derived from that superposition of theta equal to arc by radius. So you consider only SL wheel to be rotating at first. So you will get delta theta as minus delta SL by B. And if you consider only the right wheel to be rotating, then delta theta would be delta SR by B. And if you superpose these two results, you will get this expression. That's how you got this expression. Right? So, yeah. So once you have obtained expressions for delta S and delta theta, now we can get the expressions for delta X, delta Y, and delta theta. Incremental change in X position, incremental change in Y position, and incremental change in theta position. So that is defined as delta S multiplied by cos theta plus delta theta by 2. Delta Y is delta S sine theta plus delta theta by 2. And delta theta is, what we have seen here, delta SR minus delta SL by B. Right? So this is nothing but, if you multiply this with the rotation matrix, cos theta minus sine theta, cos theta, you will get the same expression, like so. So now that you have obtained this expression, if you add this vector with respect to your current estimate, with respect to your previous estimate, x, y, and theta, you will get the update for the next stage, x dash, y dash, and theta dash. And here you can consider this SR and SL to be the inputs that you are giving to the wheels. Right. So the updated position would look something like this. P dash is x dash, y dash, theta dash is P, which is nothing but x, y, theta from the previous position, plus this vector, as a contribution by the inputs, right? So this is the final expression for the new estimate. P dash is nothing but x, y, theta plus delta S cos theta plus delta theta by 2 delta sine theta plus delta theta by 2 and delta theta. This is your new estimate. Right? So that is about odometry, estimating the new position or the new location of the robot just by using the information from the inputs or information from the encoders. So notice that at this point, we are not using any information from the sensors. Right? We are purely relying on encoders, purely relying on the wheel motions. Right. So before we proceed into the next few slides, are there any questions that you would like to discuss? If there are any questions, we can discuss it now, or else we can probably move on to the summary of some more other topics. And once we have done through that, we'll discuss some sample problems. Okay, so I hope there are no questions or doubts. So the next topic that we have seen uh, for this week was something called an error propagation law. So this is where the sensors would come in, right? So one example is that if you are measuring some property from the sensor, I'll call this as theta, right? And if you consider this to be the input from the sensors, maybe input from the sensors, and then you are applying this input from the sensors into a mathematical model. I'll represent this mathematical model by this function f, and you're getting some output y. This is your output, right? And as you know, we have a lot of uncertainty from the sensor data because of the sensor noise, disturbance from other environmental factors. So like there is a lot of uncertainty associated with the measurements from the sensors, right? So if this is the uncertainty associated with the sensors, if this measured parameters has an uncertainty associated with the sensors, then what will be the uncertainty associated with the with our calculated function or uncertainty associated with the output? So this is the problem that we are trying to address in error propagation. So as you can see this equation, if this matrix Cx, if you consider that to be the error propagation, the covariance matrix representing the input uncertainties, if you're talking about sensors, the sensors would have there could be multiple sensors, right? Each of these wheels will have multiple sensors, and if this matrix basically gives a quantification of the uncertainties associated with the sensors, then the uncertainty associated with the output or for the output or the estimated position is given by this expression fx cx fx transpose, where this fx is something what we call as a Jacobian matrix. So earlier we have actually considered the model, the kinematic model of the robot like so. So the Jacobian is nothing but the partial derivative of this vector function with respect to the quantity that we are trying to measure, right? So the Jacobian matrix is nothing but if you have a vector function like this f1, f2, f3, right? And your coordinates are theta 1, theta 2, theta 3. Your Jacobian matrix would look something like dou f1 by dou theta 1, dou f1 by dou theta 2, dou f1 by dou theta 3. And the second row would be dou f2 by dou theta 1, dou f2 by dou theta 2, dou f2 by dou theta 3. And similarly for the third row as well. That is how we define this Jacobian matrix. And this term, the third term, is nothing but is simply the transpose of that Jacobian matrix. All right. So then how can we use this relation, or how can we use this error propagation into odometry? So yeah, we use this information in odometry to estimate the uncertainty of our prediction. Like, right? Because earlier we have estimated this p dash, which is nothing but x dash, y dash, theta dash, as a sum of the previous estimate x, y, theta plus the contribution due to the sensors, delta, sorry, contribution due to the inputs, delta, delta x, delta y, and delta theta, right? But as you already expect, there should be some sort of an uncertainty associated with this because, due to wheel slippages, due to wheel misalignment, all these sort of things. So, and we are basically sampling this delta x, delta y, and delta theta from this the inputs from the motor, delta SR and delta SL, right? And the way that we are estimating this delta SR and delta SL is through encoders, actually. Encoders. And the measurements from the encoders by default are always associated with some uncertainties. So the measurement from the encoders, since it is associated with some uncertainties, how would these uncertainties be propagated into the estimate of our new position? So that's what we are trying to do with this error propagation matrix, right? So we basically have this two terms actually. Yeah, we have basically these two terms. The first is due to the uncertainty in the sensors, which are the encoders, right? Not the external sensors, but the internal proprioceptive sensors. And these are the uncertainty associated with the estimation of the position itself, right? So as you can imagine, at the beginning, at the very first step, we exactly know the position of our robot, right? Because we know where we placed our robot, we exactly know the position of our robot. So at the beginning, this initial stage, the sigma p, the covariance matrix will be zero, right? It'll be a zero matrix. But this will be a non-zero matrix. This won't be a this will be a non-zero matrix because as soon as you measure from the encoders, you'll be getting some sort of an uncertainty. You can get this uncertainty measure by some calibration, or maybe it will be available from the manufacturer itself. But there are ways to determine this uncertainty from experiments directly, right? So initially this will be zero, but this term will be there. And this will be the uncertainty of the next estimate. And as in the next step, this will come over here and we'll get a new estimate over here. So like this thing runs under a loop, right? It basically runs in a loop as time proceeds. And as you can expect, at the beginning, you will have a very low uncertainty because we exactly know where we placed our robot and we know its position. So there will be a very small uncertainty. And as the robot moves along its directed path, you expect the uncertainty to grow, right? Because it gets accumulated. So the uncertainty keeps on growing and growing and growing as the robot moves. Right. So let's see what each of these terms are. Right. So these are, these terms at the beginning are some Jacobian matrices, and this is a transpose of the Jacobian. This is also some sort of a Jacobian matrix, and this is also the transpose of the Jacobian matrix. And the terms in the middle are covariance matrices. So let's see how to derive these things. So the uncertainty associated with the encoders or the internal sensors are given by this matrix, sigma theta, sigma delta is given by this matrix. So this basically says that the uncertainty or the variance, the covariance are basically independent, right? The variance of the right wheel is independent of the left wheel. So that's why we have this diagonal terms to be zero. And yeah, the covariances of left and right wheels are independent. And the covariance magnitude is proportional to the magnitude of that motion, right? The magnitude of that input itself. So that's what this term indicates. And what about this FP term? I think this term is what we have labeled here as this, delta F, this Jacobian matrix. How do we derive that, right? So a derivation of this Jacobian matrix is straightforward. Like we have already defined what our vector function would look like, right? This is our vector function. This is the model defining our kinematics. I could call this as F1, F2, F3. And the way we can derive this Jacobian matrix is by evaluating the constituent elements of this matrix, dou F1 by dou X, dou F1 by dou Y, dou F1 by dou theta. Then you have dou F2 by dou X, dou F2 by dou Y, dou F2 by dou theta. And finally, you will have dou F3 by dou X, dou F3 by dou Y, dou F3 by dou theta. So this is the Jacobian matrix corresponding to the position inputs. And this, where is this? Yeah, this is the uncertainty regarding the position. And now what about this one, this term? This term is the Jacobian matrix with respect to the inputs, delta SR and delta SL. So yeah, this one, the way that you got this expression, right? This final expression is by evaluating this following matrix, dou F1 by dou delta SR, dou F1 by dou delta SL, dou F2 by dou delta SR, dou F2 by dou delta SL, and dou F3 by dou delta SR, and dou F3 by dou delta SL. So this is a 3x2 matrix. So that is what you are getting over here, right? So once you evaluate these constituent elements, you will be able to get each of these individual terms that is being presented in this matrix actually. So we know this, what this Jacobian is, which is this one. So if you evaluate this Jacobian, you will get this matrix. We know what this is, right? Because initially this will be 0, and as the loop goes on, this keeps on get updated. So we also know this. We also know this, this will take the form like so. And if you evaluate this matrix, you will get this big matrix. And the sensor covariance also, you assume it to be proportional to the magnitude of the sensor's displacement, or the magnitude of the sensors multiplied by some scalar constant. That maybe you can get it calibrated by doing some experiments. So that is how these errors are actually propagating, and you can basically see how this, how the error propagation is going to happen. So this is how you want your robot to move in XY plane, right? This is the proposed trajectory of the robot, and as you can see, initially at the initial position there is no error, right? Because we actually know exactly where we are putting our robot, and the robot moves on its own. Once we have kept it at a position, the robot moves on its own. So as the robot moves, the uncertainty over here, gets accumulated. So as it moves here, it gets a small uncertainty. So as it moves along, keeps on getting its uncertainty accumulated as it goes on. So this is, just the motion, how the robot would move just by its odometry alone, just by using its encoders and no other insights from the external sensors. And as you can see, the variances or the uncertainty is actually very high, perpendicular to the motion of the robot, right? So if you resolve the direction as parallel to the path and perpendicular to the path, parallel to the path, the uncertainty is actually pretty low, right, by the width of this ellipse. But perpendicular to the path, the uncertainty is actually pretty high. The reason is that parallel to the path, you have a lot of measurements and you have a lot of inputs parallel to the path. But perpendicular to the path, you don't have much measurements and much insight. So that's why the uncertainty is actually growing, pretty fast, very fast, in a direction perpendicular to the sensors. Yeah. Then now that we have got some sort of a clarity regarding how these errors are building up, we use some we use some probabilistic implementation of this information from the sensors to solve this problem, right? So here and from here to here, there is no insight from the external sensors. So what you can do is that maybe if you consider, you can take a measurement here, right? When the robot is here, you are getting a measurement from the sensors. You exactly know where your position of the robot is, and you can compare that with the predicted position. And if there is a big difference, the robot can easily do the compensation. And once it has compensated, the uncertainty becomes very small, right? So when it is using the sensors, if the robot is using sensors information from the sensors here, this uncertainty would shrink to a very small value. And if it is again relying purely on odometry, this error starts to grow. And with additional information from the sensors again, whatever accumulated uncertainty it has, it will again, it will again improve on its measurements. So now we will see how we can use the sensors to reduce its uncertainty. So like we'll see what these points basically say. So using pure odometry based movement, the robot will get very uncertain about its position, right? So what we have seen over here was pure odometry. The errors keep on growing and growing and growing. So update the position using measurements from the environment. So to solve this problem, to reduce this uncertainty, we update the prediction, what we predict using the encoders from odometry using the measurements from the environment. This is facilitated by the sensors. So observation leads to an estimate of a robot's position, which can be fused with odometric estimation to get the best possible update of the robot position. So we get information from odometry, right? And then we get information from the sensors. And then we fuse both of this information to get the best possible update. We get the best possible update about the robot's new position, right? So how can we do that in a mathematical sense? So before we explain the procedure, let's look on to the parameters that are involved. So we'll call xt as the path or the current position coordinates. X, Y, Z. We call this we denote all of them collectively as xt, and ut you can consider it to be the proprioceptive inputs. The inputs that you are giving to the wheels, right? That is ut. And ZT basically represents the measurements that you're getting from the sensors, right? So we have three variables: input, you have you have the current position, the current state, you have the input that you supply to the motors, you have the observations from the sensors, and you also have a map, that is preloaded into the robot. And there's something called the belief state of the robot. So the belief state is nothing but it's the best guess of the robot's state. So it's defined by this thing that is defined by this Bayes rule. So the belief state of xt, the probability the robot position is at xt is given by the probability of xt given all the sensor readings at time t and all the previous in control inputs. So that is what we call the belief state. We also call this as a perception update because we also rely on the sensors. We also rely on the external sensors. So that's why we call this as a perception update. And there is something called belief or bell bar xt. Right? Earlier it was bell xt, and now we have this bell bar xt. So this is something given by the probability of the robot's position at xt, given the sensor readings up to the prior step. Just before the robot measures its current measurements, we don't have the current measurements. We only have the measurements up to the previous reading and all the inputs. Right, so that is what we call bell bar xt. Just before the sensor, just before the sensor reads its current position. It states a belief state just before the new observation at t, and right after the control input. So we call that as the prediction update. So like this can be demonstrated by a small illustration. Right? So if this is xt minus 1, the previous state, and this is zt minus 1, the sensor reading up to the previous stage. And you are supplying a control input into the motors ut, and the robot reaches its new position. We call this as xt, right? So bell bar xt is the probability of the robot probability that the robot is at position xt given all the measurements up to the previous time is at t minus 1 and the control input, right? So that is bell bar xt. And bell xt is after it takes its current sensor reading, right? So the probability of the robot is at position xt given its current sensor reading and the current control input. That is belief xt. So now that we have defined these probability, three probabilistic readings, we use that to, basically use that to propagate to measure the probability that the robot is in a current stage. So yeah, this is exactly what we have seen earlier. We begin with the prediction or the bell bar xt from the mathematical model, from the kinematical model, and based on the data from the sensors. The sensors will give you this delta SR and this delta SL. And based on this, it will the prediction basically give you bell bar xt. And based on the observation from the sensors, right? Whatever it is actually currently seeing from the sensors, and what it basically estimates from the map. Map basically tells it what it should be seeing, and sensors will basically see what it is actually seeing. So if both of them, the robot will then try to match it, right? What the robot is supposed to see and what it is actually seeing. So if this is basically matching, then the robot is it does not have to do any corrective measure. If it is not doing it, it has to do some sort of a corrective measure. And once it corrects itself, the position is finally matched. And once it is matched, it keeps on going on, going on in a loop again and again and again. So like these are all extracted from that lecture slide. Just to briefly explain the procedure behind prediction and perception. So prediction only relies on when coders, and perception basically relies on everything plus the current sensor measurements. So we basically deal with two different schemes of localization. So the first one we call this as Markov localization. So if you can recall from the lectures, I think the professor actually shows a very clear problem, on how to implement this Markov localization. It's actually based on probabilities. You first create a grid of position. You discretize your map into discrete grids, and at the beginning you assign equal probabilities to all these grid points, right? The robot could be anywhere within that grid with equal probability. And based on the control input and based on the sensors readings, that probability of the grid gets changed. It gets modulated. So as you do this prediction and perception update, the probability of the entire grid changes, and eventually you end up with a small space in the grid with very high probability. So that is most likely where your position of the robot would be. So I don't want to discuss that in this class, but if it is necessary, you can always go back to that lecture video on Markov localization to see that to see that numerical problem. But here, for the purposes of the session, we'll just see some salient features of Markov localization. So the features are, localization can start from any unknown position, right? If you have a map, you can deploy the robot on anywhere on this map, and the robot will start its localization based on its movement. And it can recover from an ambiguous situation, right? So even if the uncertainty is very high, or if you take the robot and if you put it somewhere in the map, it can still recover. It can still recover from that confusing position with high variance or high uncertainty eventually. So that's what we mean by it recovers. So the next point is, however, to update the probability of all positions within the whole state space at any time requires discrete representation of the space. So the required memory and power can become very crucial if fine grid is used. So this is sort of a drawback, right? So you have to discretize your map with very fine divisions, depending on your requirement. And if you want it to be very fine, you have to discretize very fine according to your need. And each of these grid points, at every update, you have to estimate the probability of each and every grid point, right? You have to keep on updating this for every iteration. And this is a computationally expensive task, right? And in that regard, it's not really that efficient, and it's computationally very expensive. So during each update, the probability of each state of the entire space get updated. So like as I was saying, for every step, for every update, all of the probabilities of each of these grid point will get updated. So initially, all these grid points will have equal probability, and eventually, as time goes by, you will end up with a distribution where the probability distribution of so some points where the robot exactly is would be of very high probability, and everywhere else is going to be very zero. And that's how the localization of the robot basically happens. So mathematically, this prediction update is defined as uh, bell bar xt, right? Prediction update is basically the probability that the robot is at xt given ut, the current input, and the previous state multiplied by belief state of xt minus 1. The complete belief of the previous state. And perception of state. The next stage, bell of xt, is nothing but the probability that the sensor is actually seeing exactly what it is seeing at this current position given its map. So as I was saying, at perception update, the robot should be see what it exactly predicted, right? So probability that the robot is seeing using the sensors what it predicted from the map is given by this probability, and that has to be multiplied by this bell bar xt. So the mathematical implementation of these two steps, the perception and prediction in a loop, is basically was demonstrated in one of the lectures of Professor Ashokan. Right. So that's about Markov localization, the salient features of Markov localization. And then we also have something called the Kalman filter localization. And the salient features of this Kalman filter localization is it basically tracks the robot and is inherently very precise and efficient. So you don't really have to discretize the grid like in Markov localization. So in that regard, it's actually pretty efficient. You don't have to update all the grid points every iteration. So in that regard, it's very efficient. However, if the uncertainty of the robot becomes too large, the Kalman filter will fail and the position is definitively lost, right? So if the algorithm is not properly optimized, if the uncertainty of the robot grows very large, it's basically not possible for the robot to recover to recover its localization or to recover its current estimate of position. Right? This thing can also happen if you kidnap your robot, from its current path, and if you try to put it in some other position, it probably it's probably impossible for it to estimate its own current position. So yeah, the working of Kalman filter is based on the principle that it basically has an uncertainty from uh, the odometry, uncertainty in odometry, right? That is defined. So uncertainty in odometry or the measurements in odometry is defined by this normal distribution n of mu and sigma 1. So if I call this as the mean of the estimate, the position estimate, and this to be the standard deviation of the position estimate. And if you have another estimate from the sensors, right? Estimation of position from the sensors as mu2 and sigma 2, this is from the sensors. So Kalman filter basically gives an algorithm for you to fuse, both of these distributions, both of these estimates to give you another distribution, another Gaussian distribution with very high probability of estimation, right? So this will be uh, maybe sigma. I'll call this mu. I'll call this mean as mu, and the standard deviation to be sigma. And as you can see, the standard deviation of that fused or the Kalman filter's output is basically lower than sigma 1 and sigma 2, right? Because of the fusion, the new variance is actually very small. And, basically you can see that from the mathematical derivation of the Kalman filter from Professor Ashokan's lectures. you probably basically see an expression like this, let me see if I can reproduce it correctly. P cap is nothing but P minus P plus R inverse P, right? So this P and R are the covariance metrics of, each of these individual terms, from the sensors and from the odometry. And this P cap is the estimate of that new output. So this thing is always going to be lower than P and R. That variance is always going to be lower than P and R. So that's the advantage of using this Kalman filter. It gives you a means for fusing the information or the distributions from odometry and sensors. And then finally, we also discussed a topic called SLAM, simultaneous localization and mapping. So like as I was saying, SLAM is a process by which a mobile robot can build a map of an environment and at the same time uses this map to deduce its location. So like earlier in all our cases, we considered the map to be preloaded into the robot. But in SLAM, it creates its map simultaneously while localizing itself. So in SLAM, both the trajectory of the platform and the location of the landmarks are estimated online without the need of any priori knowledge of the location. So essentially, it says that it simultaneously maps all the landmarks or all the features of the environment, and it also estimates its current position. You don't have to supply any prior information to the robot. Yeah, so with that, we'll solve some few sample problems. So these are mostly descriptive with very few very small numerical problems. We can solve that within the for the rest of the session, right? So if I'll be going this in a bit higher speed, because these are fairly simple problems and it's in line with what we have discussed so far. But if there is any clarification required or if there is more, if there are any doubts, please let me know by you can use your microphone or you can uh, use your chat option. Either ways is fine for me. So the first question is, given a differential drive robot which localizes itself in the environment using odometry based on wheel sensor readings. Select the deterministic errors that can be eliminated by proper calibration of system. So like we know deterministic errors can be eliminated by proper calibration, or we can also accommodate the deterministic errors into our model so that we can offset for these sort of errors. We can accommodate these errors into our modeling. So which of these models are deterministic errors? Right. So I'll go this by one. So limited resolution of during integration. So we have seen this is a non-deterministic error, right? Because we have discussed this earlier, as it depends on the sampling rate of the sensor, because we are integrating the sensor readings numerically, and you cannot you can only go so far with the sample rate. You cannot have sampling of zero width or zero duration. So no matter how hard you try, there is only up to a level that you can basically reach, and everything within that sampling rate is mostly interpolated or mostly lost. What about the uncertainty in wheel diameter and in particular unequal wheel diameter? So like we have seen that we can basically fabricate or manufacture wheels to a very high tolerance, or at least if we can measure this wheel diameter, change in wheel diameter, we can accommodate these errors into our model, right? So that makes this a deterministic error. And what about the variation in contact point of view? This is also a non-deterministic error because, the contact point of the wheel relies on the robot itself and the environment, right? And we cannot fully control the environment, right? We can only have a limited control over our robot. So that makes option C as a non-deterministic error. What about misalignment of wheels? This is also something we can basically rectify with proper calibration. So this is a deterministic error. And unequal floor contact, just like in the case of KC, that is also something not we can really control. So this is also a non-deterministic error. Right? So the question specifically asks to select the deterministic errors. Select the options that comes under deterministic error. So I hope that we have two correct answers, I think, right? Option D and option B. Right? So those are indeed our correct answers. I hope that is clear. No further clarification is required on that. Yes, the correct answers are options B and D. Now, moving on to a numerical problem. It states that for a differential wheel robot, the initial pose at A is given by the position vector 2, 3, and 25. So the position vector is given by 2, 3, and 25. This is supposed to be in degrees, right? Where this 2, 3, 5 corresponds to x, y, and theta. This is our initial position, right? And the robot moves to another point B, right? So this is point A, and the robot is supposed to move to point A to another point B. So given the distance between the two wheels as 1 unit, right? So if I draw a differential wheel robot like so, here we have the two wheels, right? So I'll label this as the left wheel and this is the right wheel. And the distance between the two wheels is given as 1 units, right? And the right and the left wheel traverses the distances which are 3 and 2.5. So the right wheel traverses a distance of 3 units and the left wheel traverses a distance of 2.5 units. So the absolute traverse distance of the robot is, what is the absolute traversing distance of this robot? Which basically means the distance moved by the robot's this central point. The question asks how much it should be moving. So as you know, if you want to know the movement of this movement of this central point, it is nothing but the height of this trapezoid or the trapezium, comprising these two displacements, 2.5 and 3. And the height is nothing but the average of these two parallel sides of a trapezium. So you can recall from that relation, delta S is nothing but delta SR plus delta SL by 2, right? This is going to be the delta S, this is delta SL, this is delta SR, and delta SL is nothing but the height of the trapezium. So going back, right, if you substitute the values, you will get 2.5 plus 3 by 2. This is 5.5 by 2. This is 2.75 units. All right, so I hope that answer is clear enough. So the correct answer is option C, 2.75. All right. So yes, that is indeed our answer. So moving on to question 3, it's a continuation from the previous question itself. What will be the change of pose from position A to position B. Right? So we know from our kinematic relations that P dash is P plus delta x, delta y, delta theta, where this P is the current position x, y, theta, and P dash is x dash, y dash, theta dash. Right? And this question basically asks you to find the change in pose. So this is the new pose. This is the previous pose. Change of pose is given by the difference between these two parameters, which is given by this vector. Right? So you have to estimate delta x, you have to estimate delta y, you have to estimate delta theta. Right? And if you can recall from the kinematic equations, which we have seen at the beginning of this lecture, delta x is nothing but delta s cos theta plus delta theta by 2. Delta y is delta s sine theta plus delta theta by 2. And delta theta is nothing but delta SR minus delta SL by B. Right? So what are the given parameters? We are being given delta SR to be, let me go back. This was given as 3.5 units. Delta SL was given as 2 units, and the distance between the two wheels was given as 1 units. Right? So with this information, we'll first solve for delta theta. So delta theta is 3.5 minus 2 by 1. This is 0.5. And delta S, we have calculated it to be 2.75 units from the previous problem. Right? Now that we have obtained that, we substitute this delta S and delta theta into these two expressions. Right? So this implies delta x to be 2.75 cos theta earlier, as per the question, was what was as per the question? Was 25 degrees. That was the theta. So this would be 25 plus delta theta was 0.5 by 2. Delta y is 2.75 sine 25 plus 0.5 by 2, and delta theta, we have estimated that earlier to be 0.5. And if you solve these expressions, I believe you will get the answers as 2.49, this to be 1.17, and this we have already calculated to be 0.5. And that makes our answer to be option C. Right? I hope that was clear enough. Now, moving on to question 4. What will be the, sorry, this is question 3, the answer. So the answer is indeed option D. Or have you made a mistake? Yeah, I think although I calculated the answer to be the correct one, I have selected the wrong choice. So just to be clear, XD is 2.49, YD is 1.17, and delta theta is 0.5. So the correct option is indeed option D. Right? Hope that is clear. Now question 4, again, it's a continuation from the previous problem. Find the y coordinate of the new pose of the robot. Right? So we know from that vector equation, x dot, y dot, theta dot is nothing but x, y, theta plus delta x, delta y, delta theta. And the question asks you to find this y, the new y coordinate. So that is nothing but you simply take the sum of the terms in the right hand side for estimating this term. So y dash is y plus delta y, and y, as per the first question, the initial first problem was 3 units over here, 3 units. So we'll keep 3 plus what was delta y as per our previous problem. It was 1.17, right? So our y dash would be 4.17 units. Easy as that. So our answer is 4.17. So this is a fill in the blank sort of a question without multiple choices, right? So yeah, that's 4 numerical questions from kinematics. Yeah, so that's about our answer. 4.16 to 4.18. Anywhere if you give the answers in between these two ranges, you would get the correct marks. Now, moving on to question 5. It's about Markov localization. Markov assumption made in Markov localization is given as, what are, out of these 4 points, what are the assumptions, that is consistent with the Markov localization. So what does the first statement say? Only the current sensor measurements are required for accurate localization. Just the current sensor measurements are required. So that is not true though, right? Because for accurate location, we need the information from the previous state. We need the estimate of the current state. Then we need the sensor reading of the current state. We also need the information from our map, right? All these information are required, not just the current sensor readings. So the first statement is obviously false. What about the second statement? The current state is only dependent on the previous state and its most recent actions and perception. That seems to be true though, right? Current state is dependent on previous state. Xt is dependent on the previous state, xt minus 1. And the input that you are giving plus the most recent sensor measurement or the sensor reading. Or we call that as perception. Anything related to the external sensors, we call it as perception. And this actions corresponds to the inputs that you are giving to the actuators, ut. Perception is zt. And the previous state is xt minus 1. And the current state is given as xt. So that does indeed seem to be valid for Markov localization, though that statement is true. The third statement is probability that the robot's state estimates equals to the actual state of the robot is maximized. It cannot be really maximized, right? It can only be given to up to some certain extent. So that is also not really false because there is always going to be some sort of an uncertainty associated with it. We can minimize uncertainty, but not fully eliminate it. So that is also a false statement. And it also says tracking the robot is inherently very precise and efficient. So from Markov localization, we have actually seen that, for every update, we have to update the probability of each and every grid points. Like even if the probability of that robot being at most of the grids is 0, we still have to update it, for every updation. So that is not really efficient, right? Because the entirety of the grid point, we keep on have to evaluate, we keep on have to compute it all the time. So that makes Markov localization inefficient compared with Kalman filter localization. So that statement is also not true. You cannot associate efficiency with Markov localization. So in that regard, our only correct answer is option B, right? So I hope there are no conflicts with regarding that answer. All right, moving on to question 6. It states state the false statements, right? So we'll go them one by one. In Markov localization, to update the probability of all points within the whole state space at any time requires a discrete representation of the grid. That is true, right? We know that the way that Markov localization operates, it requires that entire grid to be discretized. So the required memory and calculation power can thus become very important if a fine grid is used. Obviously, that is a true statement regarding Markov localization. And option B states Markov localization starts from any unknown position. So that is also one of the defining features that we have discussed in Markov localization, right? It can start from any position. You can, kidnap the robot from current position and place it somewhere else. It can again begin its localization from the new position. That is also true statement. And option C, in Markov localization, the recovery from ambiguous situations is not possible. That is false, right? Because like we know the probability of the entire grid. So like even if you kidnap the robot from one position and put it in some other position, it will still have some estimate of the probability that the robot estimate of the probability of the position of the robot. So that is false. It's recovery is impossible for Kalman filter implementations, not for Markov localization. So that is false. And option D states a Markov localization tracks the robot and is inherently very precise and efficient. So like just like what we have seen earlier, this is a false statement. Efficiency cannot be associated with Markov localization. So that is also false. And the question says to select the false statement. So there are two false statements, which are options C and D. Yes, that is quite correct. C and D are false. Yes. Yes, C and D are false. Now moving on to question 7. For a robot moving in negative y direction in the global coordinate frame, uh, and which uses control input to predict the position estimates. For such robot, the position estimates will have uh, variance equal in x and y directions, least variance in direction orthogonal to the motion, least variance in the direction of its motion, and variance will be greater in y direction. Right? So we have seen earlier in odometry, right? If a robot is moving in one direction, so like as per the question, it says negative y direction. So let's say this is negative y direction, right? And at the beginning, the uncertainty is actually let this be some other direction, something else. Let this be y direction. So we consider the robot to be moving along the negative y direction. And if you can recall the chart earlier that what I have produced, the ellipsoid depicting the uncertainty. Initially, at the beginning, uncertainty is very small. And as the time goes by, the uncertainty keeps on growing, higher and higher and higher, like so. So what can we infer from this uncertainty ellipsoid? So let's go by one of the options. Variance equal variance is equal in the x and y directions. So if you consider this to be negative y direction, let's consider to be this axis, this vertical up and down axis to be x-axis. Doesn't matter if it is negative x-axis or positive x-axis. The first statement says variances is equal in x and y directions. But as you can see, how that covariance matrix evolves, it's not equal, right? There is low variance along y direction and high variance along x direction, right? So that is equal variance is not an option. What about statement C? Least variance in the direction orthogonal to its motion, right? So the direction of motion is along y-axis and orthogonal to the motion is x-axis. And the statement says least version in the direction orthogonal to the motion. So it's not the case, right? We have high variances in x-axis and very low variance in the y-axis. So that the second statement is also false. What about option C? Least variance in the direction of its motion. So if y-axis is the direction of motion, you can see that the width is actually very small in y-axis. So that is a true statement. Least statement in the direction of motion. Option D is variance will be greater in y direction. That is obviously false. Variance will be lower in y direction. Right? You can basically reproduce this sort of chart in MATLAB or any other software. If you implement that error propagation law, error propagation due to the uncertainty in position and uncertainty from the encoders, if you run that in a loop, and if you plot the uncertainties in both axes, x and y axes, you will get something like this, very similar like this. So here as well, the correct option is only option C. I hope that is clear enough. Yeah, this is what I was talking about, right? If the robot is moving in one direction, in this case, it is moving along x direction. The uncertainty in x direction is very small, but uncertainty in y direction is actually very high. Okay. Now moving on to question 7. For a robot moving in, okay, I think this is just the question that we have seen. The solution is indeed option C. Moving on to question 8, choose the incorrect statement. So the first statement is SLAM is a process by which a mobile robot can build a map of an environment and at the same time use the map to deduce its location. So that is true. By definition, that is true. By definition of SLAM, that statement is indeed true. And the second statement is in SLAM, both the trajectory of the platform and the location of all the landmarks are estimated online without the need of a prior knowledge of the location. That is also true from the location of something. Okay. Now, yeah, you don't need to supply any prior information for SLAM because it simultaneously gathers all the information from the map, all the landmarks from the map, and it also localizes itself as it creates its own map. And statement C says SLAM stands for simple localization and mapping. So that's not true, right? SLAM is basically simultaneous localization and mapping, not simple as given in the question. So that is false. Option C is false. or incorrect. Option D states in SLAM, only the trajectory of the platform is estimated online with the need of a priori knowledge of the location. So like B and D are basically contradicting. We have essentially, we know by definition that this is a true statement. For SLAM, we don't have to provide anything prior, right? We don't need to provide any prior information about the location. It estimates on its own. So that is also indeed false. So the incorrect statements are option C and D for this question, because question asks you to find the incorrect statements. So C and D are incorrect. All right. So moving on to question 9, we have a couple more questions. Choose the correct statement that best suit for prediction update of a robot. We have seen two cases, prediction and perception. Right? Prediction relies on estimation of new position from the control inputs to the motors and current position. Right? Whereas perception is everything from the prediction plus sensor measurements. At the current time or at the new location. Right? So the question asks you to choose the statement that best suit for prediction update of a robot. So the first statement says estimate the current position based on the previous position and odometric input. That is true, though, right? That is true, indeed true, because it tries to from the previous position, if it knows its odometric input, odometry consists of the previous position and the control input, you estimate the current position or the new position. So that is prediction update. We don't do anything about the external sensors at the time for prediction. Second statement says predicts the current position based on previous position and sensor input. So that is indeed false, because prediction does not have anything to do with sensor input. Then predicts the current position based on previous position and previous uncertainty. That is also not exactly true. That is also false. And option D says estimates the current position based on odometry and sensor input. I think option B and D are essentially the same, right? Previous position also comes under odometry. Previous position plus control input. So those two comes under odometry. And sensor input, we don't have anything to do with sensor input for prediction. So that is also false. So the only correct answer in this case for prediction is option A. Everything else has something to do with perception. And question 10. Given a differential drive robot which localizes itself in the work environment using odometry based on wheel sensor readings. So like you have a differential wheel robot with wheel sensor readings that relies purely on odometry. Select the correct statements from the following. Okay, the first is non-systematic odometric errors can be eliminated by proper calibration of the systems. So that is false, right? By definition, we can only eliminate systematic errors. Non-systematic errors or random errors cannot be eliminated, but we can somehow model it using some probability distribution. So the first is indeed false. The second statement is the drawback of using just the odometry for localization is that errors are integrated, leaving no upper bounds for errors. So that is indeed true, right? So like as you move along just with odometry, you can see that the uncertainty is actually growing. And if you integrate, if you integrate all these estimates, once the robot reaches its final position, the errors will all get accumulated, and there is no real upper limit for these sort of errors. It will grow unbounded. So the only way that you can limit these errors is through using periodic sensor measurements or periodic inputs from the sensors. So that is indeed true. The second statement is indeed true. Third statement is non-deterministic errors are random errors. That is true. They have to be described by error models and will always lead to uncertain position estimation. That is also indeed true, right? You cannot accommodate non-deterministic errors into the model. You have to have, you can model them by some probability distribution, but you cannot exactly model them. And, you cannot try and compensate for these errors. So that is indeed true for random errors. And the fourth statement is variation in contact point of wheels, unequal wheel diameters are non-deterministic errors and cannot be eliminated. That is false, right? So issues with wheel diameters, we can, we can, our fabrication methods are very well matured so that we can have wheel diameters of very close tolerances. So that should not be an issue. So like even if you don't have access to, even if you don't have access to high quality fabrication methods, we can simply measure the wheel diameters and we can basically accommodate or we can compensate for these errors in our models, with the measured wheel diameters. So that statement is indeed false. And as a result, the only true statements are options C and D. These are just the two statements. All right. So yeah, options 2 and 3 are only the correct answers. I hope there are no conflict regarding that. I think, yeah, moving on to, I believe we have reached the second last question, or second to second last question. So the belief state calculated before the new observation at T, just after the control input, is defined as. So like we have seen, as per the definition, we have seen two cases basically, right? We have seen bell bar xt and we have also seen bell xt. If you can recall, we call this as prediction update and we call this perception update. And this is just before the sensor reading, just before the sensor reading or the current sensor reading, but after the control input. And this is basically, everything else what I have said, but after the sensor input, after the current sensor input. So the belief state that is calculated before the new observation, before the new observation is bell bar xt, which is basically the probability of estimating the current position with our previous estimate and the control input. And that too right before, before incorporating the measurements from the sensors. So that is Before the new observation, that is nothing but the prediction update. That is option C. So like, I hope we can all agree on that without any conflict. For question 11. Yes, it is indeed option C. And moving on to the second last question, choose the wrong statement from the following. Choose the wrong statement from the following. Okay. So due to the discrete representation of grids, Markov localization is computationally expensive than Kalman filter. So we have discussed this numerous times. We have come across this point numerous times. So that is indeed true, right? Markov is computationally more expensive than Kalman filter localization. Second statement is, sorry, I'll just label this as true. Second statement is Markov localization is capable of recovering from ambiguous situations. That is also a true statement as per the definition of Markov localizations. The advantage of Kalman filter localization over Markov is that Kalman filter is more robust than Markov. That is actually false, right? If you can recall from the definition, Markov localization cannot recover if the uncertainty is actually very high, right? So if you kidnap the robot from the current position and if you deploy it in some other location, it will have a very high uncertainty because of that sudden change in position. And in Kalman filter, it cannot recover the localization or it cannot recover its current estimate of position if the uncertainty is actually very high. So if that is the case, you cannot actually call it robust, right? Robust means whatever happens, if you kidnap the robot or if you abruptly force the robot to change its position, it should still recover its estimate of current position. So that makes Markov to be more robust than Kalman filter. Kalman filter cannot be called as a robust filter actually. So that's the reason why we call it to be a false statement. And the fourth option is Kalman filter localization models measure noise as Gaussian distribution. That is also true by the definition of the Kalman localization or by the assumptions that we make in Kalman in defining the Kalman filter models. And the final statement, Kalman filter localization is inherently more efficient than Markov localization. That is also true, right? Because Markov discretizes the grid, and as a result, the probability of each and every point of the grid has to be updated every time for Markov, but that's not the case for Kalman filter localization. So the question asks you to find the wrong statement, and the only wrong statement is option C in this case as well. All right. So that is indeed the solution. Correct answer is option C. Moving on to the final question of our session. So the blank is a process by which a mobile robot can build a map of an environment and at the same time use this map to deduce its location. So what option is this going to be? Is it perception, localization, mapping, SLAM, or prediction? So this is a fairly easy choice. A process which it can use to build a map, and at the same time, it can estimate its own location, simultaneous map and localization. That by definition is SLAM, simultaneous localization and mapping. So this is indeed our answer for that option, because SLAM is the definition, the most appropriate definition for this statement. All right. So with this, we can wind up the session for this week, for week 5 content. Next week, we'll discuss about navigation, some navigation algorithms. And on the subsequent week, we'll discuss more on design of motion controllers. Okay, so that's about it from my side. Uh, if you have any questions, please let me know. If there are no more questions, okay, thanks for joining. Thanks for joining for this session. Hopefully, we'll see next week. You can log off. Thank you. Thank you very much. Thank you.